Ай, Володя. Кажется, только мы два.
Oh, hi, Ian.
Hi. It's funny, it's only me and you.
How are you doing?
Oh, I'm okay, thank you. And you?
Well, I'm fine, thank you.
You're in France?
Yes, I'm at HS now.
Ah,
You see. You are in Moscow or in England?
yeah, I'm afraid I will probably never manage to leave this place.
Ah, I see.
But I still survive.
Здравствуйте, Володя.
Hi, Gosha.
Oh, hello. Sorry, just probably had to speak English.
No, I mean, пожалуйста, общайтесь по-русски.
No, it's okay. Can I share my screen? Or...
Sure, of course.
Now you will have a whole new audience. Suddenly you have many.
Привет. Здравствуйте.
Здравствуйте. Еще раз всем.
I don't understand what's happening.
Пока не видно вашей презентации, Володя.
Yeah, I'm trying to do it. No?
No slides are still visible.
Ah, I see. Sorry. It's my fault. I forgot very important thing. So now it's okay?
Yeah, now it's great.
Do you see what I'm doing?
Yeah.
Okay, you just give me the command.
Саша, подождем немножко еще. Я думаю, что, может быть, придут кто-то.
Хорошо.
Да, несколько минут.
Yeah, it's possible that some of our other participants will join.
The students, maybe.
Yeah. Значит, Володя, я отвечал на вопрос, сколько времени. Значит, что anything from 1 hour to 2 hours is okay. Anything.
Well, you can stop me at any moment.
Okay. Hey, what time is it? Okay, we can wait for another couple of minutes just to make sure that everybody who wants to join has joined.
Do you know how I can make the full screen mode?
Actually, it depends on the file you choose, actually. I don't know what kind of file you use here.
I see. I can't.
Usually you can just, well, in PDF, you can just choose this full screen mode, but is this PDF?
FNF.
Oh, I'm sorry, download. I'm not familiar with this type of files, unfortunately. It seems that nobody is going to join us.
I don't understand why I can't do it.
Actually, I am in full screen mode now. With my laptop, everything is full screen mode. There are only a couple of, yeah.
So they know how to do it. If you share your screen from your iPad,
Oh no, I don't have iPad. As far as
I see.
I cannot. I'm not an expert in the iPads, unfortunately.
Point.
Okay,
Anyway, if it is visible, it's okay. It's visible for you.
as far as I'm concerned, everything is perfectly visible. Not a single problem with it.
Okay.
I don't know. Oh, it seems that it was not in vain that we were waiting for other participants. I can see some Chinese guy joining us.
Yeah.
Yeah, Junhu is here.
Gosha, will your students join the seminar?
Actually, he has received this. He said that he is quite busy until the end of March this year, so probably Jaran. I mean other students.
Yes.
They all received this. They all received this.
Okay.
They don't know why they're not joining. I was sure they would really love to see it, but okay. They probably join later. They might be just getting late.
Okay, then I think we can start.
Yeah. So it is my
So I
pleasure.
speak English or I should speak Russian? Tell me, please.
Actually, there is one Chinese student present at our seminar, Junhu Guo.
So there are some students in the audience.
Yes.
Yeah.
Okay. Don't worry. I can speak English.
So it is my pleasure to introduce today's speaker, Vladimir Rubtsov from University of Angers, France. Very well-known expert in the field of integrable systems and in geometry. And he's going to talk about higher Bessel kernels, Buchstaber and Kontsevich polynomials, and beyond. Well, beyond is the most intriguing part, I believe. So let us take a look at this.
Okay. Do you hear me?
Yeah.
Yeah. Thank you very much for your invitation. Thanks to everybody for coming. I will speak about some activity in which I was involved in mainly in the last few years. And this is, in fact, a very, very big piece of different domains of mathematics, from number theory to special functions and algebraic geometry, and including harmonic analysis and even combinatorial ideas, theory of polytopes, many things. And I will try to discuss only one piece of this activity, which is based on our work in progress in two different group of co-authors, which in one group, Ilya Gayu from Toronto, and Duke van Straten from Mainz, and myself, and in another, again, Ilya Gayur from Toronto, Viktor Matveyevich Buchstaber from Moscow, and again, myself. So we, even these two groups, they cover it, and two papers in progress, which I hope will be very soon, very soon ready to submit to archive at least. Even these two papers, they don't cover all branches of this possible activity, and there are some open questions, there are some interesting problems. I think it would be nice if young people draw their attentions to this area. And one of my aims just to stress this fact. So my overview will concern so-called modified Bessel equations, or more precisely, these equations and solutions of these equations, even not exactly modified, but differ from modified Bessel by sign. And this is important because this modification of modified Bessel plays a principal role in quantum theory of differential operators, Dubrovin, Giventhal, and other people. And also there are some very important number theoretic correspondence between this type of equations and so-called solutions of these equations and so-called Klosterman exponential quadratic sum for two bases and higher exponential sums in number theory. And the second part, what I want to discuss is very simple object, two families of polynomials, which it was my observation and my name. I mean, I gave this name to this family of polynomials, Buchstaber polynomials and Kontsevich polynomials. Moreover, it's a generalization of initial Buchstaber and Kontsevich, and I want to describe these families, and in fact, to argue that in fact it is the same family in different facets. And then, if I have time, I will briefly describe some importance of these two subjects. So, first subject of my talk, as I told you, this n Bessel or Pn-1 quantum differential operator. And this is an equation. This quantum differential operators, they are very important ingredient of the mirror symmetry program, which was developed by Giventhal, Yao, and many other very famous mathematicians. This part of this story was developed and based on the ideas of Boris Dubrovin, and so-called gamma conjecture of Dubrovin was proven for special types of manifolds by Vasily Goloshev, Don Zagier, Alessio Corti. Many mathematicians proved it for Grassmannians, for Feynman manifolds. So I will speak about only very simple analytic and special function aspects of this operator and this equation. Second, what I want to show you, this is what I called Buchstaber polynomials. This family of polynomials, you see, it depends on three variables, x, y, z, and three parameters, a1, a2, a3. And to save place, I wrote it in basis of symmetric functions of x, y, z. So sigma 1, it's just a sum. Sigma 3 is just a product. And sigma 2, it's a sum of pairwise products of x, y, and z. Of course, I will show you full formula a little bit later. What is important, a part of this observation that this polynomial family depends on symmetric functions of x, y, z, that you see, I wrote it in the form of some discriminant. So you can imagine that there is a quadratic function for a polynomial function for which this family plays a role of discriminant. So it's like b square minus 4ac. So it is discriminant type polynomial. But it is not the last beautiful property of this polynomial. Also, if you write this as a function of x, y, z, this function will be, of course, general degree 6. But considering as a function of each single variable x, y, and z, this function is always quadratic. It means that you can present, for example, this like a function in z squared plus qz plus r, where p, q, and r functions of x and y, and the same for each other two variables. So you can compute discriminants of this secondary discriminant. So it is discriminant as per se, but also you can compute for each single variable, you can compute discriminant. And you will find a miracle that this discriminant is splitted. It means that it can be presented as a product of two identical functions, each of different variables. So if you consider discriminant in z, so you have a product of some function f and in x and some function f is the same function f in y. So it is such polynomials were studied by Volodya Dragovich. Some of you know him very well, and he called it weakly and strongly splitted, discriminantly splitted polynomials. Weakly, it means that you can present it just in the product, and strongly if you can present it in the product identical functions. So this is very important ingredient of his analysis of integrability of Kovalevska talk. Then second family, the last hero of my talk today, it's a so-called generalized.
Sorry, can I ask a question?
Sure, you can interrupt and ask at any moment.
Okay, why they are called Buchstaber polynomials? So I understood.
That's a good question. Thank you very much. Good question. These polynomials, it is just I wrote it in nutshell form, if you want. But initially, these polynomials were discovered by Victor Buchstaber in 1990 when he studied special, when he wanted to find a special description of elliptic group law of special formal elliptic form, two-valued elliptic formal group law for special type of formal groups. I will speak about it a little bit later. And then he discovered that each such polynomial, if you have special value of a1, a2, a3, define or not define good two formal elliptic two-valued group law. That's why I called it Buchstaber polynomial.
Oh, okay. And AJs are just some complex numbers, right? Or
A2, yes, it's just three complex parameters.
okay.
And the generalized Kontsevich polynomial, they are also very nice polynomials. You see, first of all, it is also discriminant type polynomial because I wrote it like a discriminant with respect to some variety t. And this polynomial has the form discriminant of this quadratic polynomial with again symmetric dependence of x, y, z, and C complex parameters a, b, c. What is written here, in fact, I will not say hide something. I will write you this explicitly. Let's consider a polynomial in T, which is different of this monic cubic polynomial minus t minus x, t minus y, t minus z. So being monic, this term t cube and the minus t cube will disappear, and you obtain this polynomial a plus x plus 1. I think it is. I just made a mistake when I typed it. Sorry. No. I didn't. Everything is okay. No. So now I write the polynomial. I write this polynomial. So I have this square. Means sigma 2 minus b square minus 4 a plus sigma 1 sigma 3 plus c. And this is what I denote P, A, B, C Kontsevich generalized polynomial. First of all, why it is Kontsevich, and second, why it is generalized. Kontsevich described this polynomial in his famous paper in 2007. This part of the story is very, very interesting, and I probably needs at least 1 hour or 2 hours to describe. He wanted to understand the structure of Hecke operators in the case of automorphic forms over finite fields and in function fields over finite fields characteristic prime characteristic. And description of these Hecke operators, it leads him to a conjecture that number of such operators can be counted by some discriminant type polynomial. And for special values of A, B, and C, namely he used C equal to 0, A equal to -1, and B minus T, and B equal 1 plus T. Then you obtain the family of one parameter. Sorry, it is not the same T. Let it denoted by another letter. It's not T, because T is free parameter here. Let's denote it by Z and Y plus Z. So Kontsevich polynomial, it's polynomial of minus Z, 1 plus Z, 0. And then in his conjecture,
is also a bad parameter.
Hmm?
Z is also a bad parameter because it's used in the polynomial. Perhaps tau is better.
Okay, better. Okay. Great.
Z is one of the
Good
very
remark. Good remark. Tau and tau. Yes. Tau and tau. I will not go into details, but I want to say that very real correct form. Of course, this polynomial was an important ingredient, but real number of Hecke operators needs some correction. It means some additional term to this polynomial in the Kontsevich formula. But this correction term, it is not, it is some constants for special cases. They were computed by PhD students of Duke van Straten in 2019 exactly. But before, in master thesis of Drinfeld student Tiruji Thomas, he also wrote correct formula for this number of Hecke operators. And then a more general form of this were proposed by Anton Melit and Vasily Golyshev. And then in 2011, I joined discussion with Vasily and Anton from absolutely different perspectives related to some separation of variables of integrable systems, which we proposed long time ago with Benjamin Enriquez. And then in our discussions, we just proposed more general form of this polynomial, very slightly more general, but it is put some things in its proper place. And probably 3 years ago, I had some very simple conjectures that there is a link between Kontsevich and Buchstaber polynomials. And then it was the origin of my proposition to unify these polynomials in one family. I will formulate a very simple theorem at the end of my talk, which relates Kontsevich and Buchstaber polynomial and put it in. Roughly speaking, I can say that they are in the same orbit of the of some natural action of Möbius group.
So just to summarize. Just to summarize, Kontsevich polynomials describe the number of Hecke operators, right? Of
Yes. Yes.
And Buchstaber polynomials appear from some
rules, some govern some formal group law.
And is there any general will you describe any kind of
Yes, there is a background, common background why it is not very exciting. Even in the paper of Kontsevich, he understood that there is a because Kontsevich proposition was not universal. It was for very special. It was a kind of Langland's conjecture. Interpretation for very special type of local system, namely for sphere minus 4 points. Yes, and sphere in the case of finite field field with characteristic p. And then you can easily understand that behind of this p1 minus 4 points there is some elliptic curve which is covered. And this elliptic curve should play some role in the construction of this two formal group law, which Buchstaber, I don't remember at which year, called it two-cassette construction. So with the help of this elliptic curve, one can construct a formal law. In the case of Kontsevich polynomial as well. And then it is not strange that people want to unify it in some sense, or at least understand how they express one via another. And the answer is very roughly that they are transformed one to another by some Möbius, very simple Möbius transformation, namely by inversion 1 over x, 1 over z, 1 over y. Yes, and also this transformation, it's a kind of, if you consider this in projective coordinates, it will be kind of Cremona transformation.
Yeah, thanks.
Yes, but there is also another unification. This unification, which from my viewpoint, the most beautiful part of the story is this unification that both polynomials enter in so-called theory of multiplication kernels. It's a classical part of analysis which is known since the 19th century. People studied such problems very, very intensively. And what I understand under multiplication kernels, this terminology was proposed by Maxim Kontsevich. And roughly speaking, you have some family of functions which depend on variable x and parameter lambda. You can imagine that these functions, just for simplicity, you can imagine that these functions are eigenfunctions of some operator. I don't care about this operator at the moment. Equal to lambda 5. And you have this psi lambda is a solution of this problem. And we suppose that if you have these functions, eigenfunctions, with the same value lambda in point x and in point y, you multiply these two functions, and we suppose that we can express it in terms of some integral form via the same lambda eigenvalue, but in the point z, where z is an integrable measure, and some kernel functions, some kernel function. This kernel function doesn't depend on, it is important, doesn't depend on lambda. So, and over some cycle gamma, it is at the moment I don't care about.
Just to clarify the notation, what does it mean when you use this y bar z notation?
You integrate by z, just. You can imagine that you have on the set of these eigenfunctions, you have some algebraic structure, and this kernel plays a role of associativity constant. It's a commutative algebra, and the associativity constant, it is of course not a strong statement at this point, but I will show you some examples where.
No, I mean, what does this notation mean? Y bar z.
It means that z is a special. It's a difference between it means that x and y it's external variables, and z it's a variable of integration. That's all. Nothing.
I see.
And the kernel K does not depend on lambda, right?
Doesn't depend on lambda. This is important. Yes. Okay.
K symmetric with respect to x and y.
Of course. Yeah. It's commutative object. Now, first of all, such classical formula for so-called duplication Clausen formula for Gauss hypergeometric function with parameters a and b in our numerator, and a plus b plus 1 over 2 in the denominator when you write it in the form of infinite series. Then if you take the product of these two functions, Clausen in 1828 defined, proved this, and his paper just was, it was, I never saw the paper which was named by the main formula. He called his paper this square equal to f32 and etc. It was just the title of his paper. And it is possible to find in Krell journal copy of this statement. And the second formula which I want to show you, which I will discuss it a little bit later in different form. It is so-called Schlafly confluent formula for hypergeometric degenerated function when you have this 0f1 function. If you have this degenerated hypergeometric function 0, 1 with parameter n, no parameters in numerator, it means 1, and in denominator you have gamma of n over 2 plus 1, and variable nx over 2, and then the same function in the point y, then the product of two such functions, when you can represent by beautiful integral formula, and this beautiful integral formula, it's integral over a sphere. Sorry, I want indicator, not. I want indicator, not. This one. And this integral of the same degenerated hypergeometric function, but with the same parameter n over 2, but the variable of this function, it's a scalar product, and this scalar product, it's a scalar product which you should compute over n-1 dimensional sphere. D mu, it's invariant spheric measure. E1, it's just one 0, 0 vector in corresponding R to N Euclidean space. And this multiplication, one can be interpreted like a commutative coalgebra of functions on R to N, well, continuous and invariant with respect to action of this orthogonal group on R to N. So this formula, of course, without mention of commutative coalgebra structure, was discovered by Schlafly in 1876. He just wrote this in hypergeometric function form, and this x and y, they are vectors on sphere. So x, it is just norm of vector. It's a square of norm of vector on sphere. Y, it is square of norm of vector on sphere. This is just a multidimensional analog of cosine theorem. This is a product of norm, and then you have this beautiful multiplication formula. So this you can still here you don't have a exact appearance of kernel, but you see that it looks like some algebraic structure. In fact, it's co-algebraic structure. Buchstaber and Kontsevich, they discovered that when n equal to 2, in this case, when you parameter n equal to 2, then in this case, you have a real two-valued cyclic formal group. For other values of n, it is not a formal group, it's only co-algebra. But another interpretation of this formula was because people didn't connect it with internet, and they didn't contact it very much. Almost in the same time when Schlafly proved it, and he was from Vienna, and Schlafly was from Basel in Switzerland. And in the same time, Russian mathematician Sonin and Austrian mathematician Gegenbauer, they proved another beautiful product formula. Namely, they took 0 the Bessel function of degree 0, usual Bessel function, not modified. And if they multiply these two functions, they were able to write it like an integral of Bessel function of z with measure z dz divided by some algebraic expression, which is very, very nicely polynomial, has very nice polynomial form. And this nice polynomial form, not just occasional. You will see that this is a special case of Kontsevich polynomial. Namely, let's consider the construction which I described you before, and consider so-called D2 or Hoyne equation. It's a special kind of Hoyne operator. Take function f, which with monic cubic polynomial with free term equal to 0 and term in front of t equal to 1. So with one parameter a, it is a special part of Hoyne, special case of Hoyne operator. And then apply this construction which I described. Namely, take the discriminant of the difference between f and t minus x, t minus y, t minus z. Then we obtain this special kind of Kontsevich polynomial. And the theorem, which we knew and we proved it in our paper with Goloshev and Melit and Van Straten in 2021, that the product of these functions, eigenfunctions of this problem with Hoyne operator corresponding to f. So it's d f d plus t, and this is an eigen problem for this operator in the bracket.
So,
So the product
what does this circle mean in between dt and f in this formula?
just a composition.
Just product by ft.
It is just no. It means nothing. It's maybe not very good notation, but it means that you take d.
Mm-hmm. Multiply the result by ft.
Yeah, you just take d f d. That's it.
I see. Mm-hmm. Thanks.
When you applied it to some function phi, you just apply d, then f, and then apply and use a Leibniz rule as usual. You see.
Yeah.
So it's a second order operator with a prescribed type of singularities and the unipotent monodromy, which at the moment it is not important. What is important that you can write it in as a multiplication kernel form. So first of all, the question when this multiplication kernels can be described for some kind of for some class of differential operators, for some class of examples. This the answer to these questions was done by Kontsevich and Sasha Adesky almost after our paper with Goloshev and Van Straten and Melit, and they wrote a long paper with an enormous amount of different multiplication formulas. But for some reasons, I don't know why, they missed the most simple and most beautiful computation.
Sorry, just one question. This formula you wrote, the last formula, it looks pretty much like the addition formula for elliptic functions or something like that. Is it?
Yes. Yes. Oh, so absolutely. If you put here instead of Kontsevich, if you put here Buchstaber polynomial, you will obtain some addition formula. That's yeah. I will speak about it.
Okay. Thanks.
So they didn't consider in details the most simple and most beautiful case, the case of N-Bessel operators. First, I will because I was supposed to speak in details, now I want to start with the observation. And this observation was that kind of pseudo-philosophical observation that Bessel functions, you should think about Bessel functions like about non-abelian version of exponential function. That's our philosophy, and I want to show you some arguments for this philosophy. What is a one Bessel function? One Bessel function, it is just usual exponent, nothing more. Let's consider this logarithmic derivative xd over dx, which is popular for people who are doing number theory and algebraic geometric aspects of mirror conjecture, and consider eigen problem for this operator xd over dx, for this operator theta. So this operator theta minus x, and lambda is just eigenvalue. Then it's very easy. It's just the first year probably in school answer for this question. What is a psi? Psi is just exponential of lambda x. So we can represent it in series over in the x and with the parameter lambda. And multiplication formula for exponent gives you that it is a addition of x plus y times lambda in the exponent of this exponential. And we can present this in integral form with the help of delta function with respect to z in the point x plus y. So if you take exponent lambda z, then you evaluate this exponent lambda z with the help of this delta function in integral form, or otherwise you can represent it by Cauchy theorem as a residue over z in the circle with radius x plus y, and the kernel, Cauchy kernel, it's 1 over z minus x plus y. And you see, it is even this representation, it is some rational function, not very trivial, which gives you example of the kernel multiplication type. Even more interesting the case of two Bessel operator. Two Bessel operator, it's the operator when operator theta in degree 2, and we consider again eigen problem for this operator. This eigen problem has known to you this degenerate hypergeometric function, which people denote G0 x lambda, or it is a usual Bessel function, or you can use it in modified Bessel function after change of variables, some change of variables. And this function can be represented also as a series, but now you have not exponential, but you have degree 2 in the denominator. Integral representation for multiplication kernel here, it is very famous Sonnen-Gegenbauer, as I told you. And this Sonnen-Gegenbauer formula has this analytic algebraic expression. You remember that I made some mistake. This mistake is the following. It's a mistake that I made this change of variables. So you should write this not G, you should write this E. Because when you write G, as before, I will show you. When you write this G, then you should put in the measure Z, and under a radical, you should put degree 4. It's very important. And products here contains degree 2. But when you go to this change of variables in Bessel functions, and you take modified Bessel, E0, then this product is without Z here. And under radical, you have quadratic expression. So the zeros of this kernel function, it is a conic. This is beautiful conic. You can find it almost everywhere. Almost everywhere. It means that you can find this conic.
Sorry, then there should be also Z in the numerator, right?
Sorry? Z?
Yeah.
No, that's what I told you. Z, if you take usual Bessel function, this one.
Yes.
But
you put square inside. Okay, I understand. Yeah.
I will show you this computation.
Okay.
And also you can check that this kernel K satisfies some differential equation. First of all, this differential equation has order 1. This polynomial under radical in front of d over dx, it's zeros of these polynomials, they are singular points. And if you take x equal to 0, then your polynomial becomes rational. So this is what people knew when they studied special functions for two Bessel. It means that Sonnen, Gegenbauer, and Bailey, British, very famous British analyst, and of course Watson, who wrote a 2-volume book about Bessel function. He knew these formulas very well. Now, I want to draw your attention that if we take the diagonal, it means take x equal to y, then we consider this Bessel solution, and square of this Bessel solution, it means we take the product J0 times J0. In fact, again, it is not J, it is E. I'm sorry, it's again E. Because for G, it's a little bit different formula. Then this Clausen duplication formula can be written in integral form. Of course, it is special form of Clausen duplication. Initial Clausen, it was for non-degenerate Gauss hypergeometry, and this Clausen for degenerate F01. But if you look attentively on this integral form, you will find that the kernel for which we wrote it, this kernel has beautiful series, and this series it is a binomial, central binomial series. And this central binomial series intimately connects with Clausen, with Catalan number generating function.
I'm just a little bit confused. It seems that the convergence radius here is...
Sorry?
I cannot see. The convergence radius here seems to be pretty small. I don't understand. So it's 2n factorial on the top, and then in the bottom you have n factorial square, right?
You mean,
Yeah, this binomial coefficient.
yeah. So what?
I mean, doesn't it go to infinity? I really have, I just don't understand if
No, it's
the convergence radius seems to be pretty
no, it's
small.
good enough. Why? It's 2n. It's good enough.
I mean, the convergence radius seems to be like,
It is 2 times n to n
It's
factorial.
not 2n factorial.
Huh?
It's not 2n factorial. It's just you need to use the
like if I forgot.
formula.
It's
So where do you put this? I don't quite remember this. I used to think that what you have in the top goes in the numerator of this binomial coefficient. I just don't remember this
You've
notation.
got a missing in to the power -1, maybe. You've got
it says n over k. It's n factorial over n minus k.
Yeah, but he's just
Yeah,
pointing out
precisely.
that this coefficient tends to
So
infinity.
it's c to n n. Yes. This one.
So in the top you have n factorial.
Yeah.
So in the top
Yes.
here you have 2n factorial divided by n factorial squared,
Yes.
but that goes to infinity.
But in the denominator. Why?
Not then.
Do you
mean,
want to divide by it, Volodya? Have you forgotten
Yeah,
the
it's
exponent
the minus
-1?
first,
Maybe that's
probably.
the reason.
It's reciprocal of this binomial coefficient.
You mean it depends how you define this.
Yeah, I mean the coefficient is growing. That's
This
You're
one-
just making the simple observation that this coefficients tend to infinity. Even I can see
Yeah.
them.
This coefficient.
yeah goes to infinity.
2n factorial
Yeah.
divided by n factorial squared tends to infinity.
And pretty rapidly, I would say.
Maybe I wrote.
This must be a misprint somewhere.
Yeah.
Because obviously
Maybe-
the left-hand
maybe-
side is a nice function. So
Yeah. Okay.
Okay, maybe it's just I can check. Okay.
Mhm.
Sorry. Yes, I understand what you mean. But it is very strange. Maybe it's a wrong notation. You propose that this should be n over. What I'm saying?
Something like that, maybe. Just 1 over this binomial coefficient.
Okay, I will check. I will check. Let us go further. I can check. Maybe it's really bad notation.
There should be probably 2 power n, not 2 dot n, but 2 power.
No. No, it's just central binomial. It is like this, but maybe it is just a misprinted notation. Okay, I understand what you mean. Okay, now I want just to precise. Maybe we will even understand it more quickly. This is a standard Bessel function, which I prepared in details with. I'm just sorry, I want again to use this. Standard Bessel function contains minus, and then we take this equation. This is a standard Bessel equation, which is solution. It's analytic solution. Just don't forget that Bessel equation has two solutions. One solution is analytic and zero, and second solution is not analytic. It contains logarithmic terms as well, and it denotes by k0. it is also a beautiful function, but it is not the hero of my story here. And then if we take this change of variables, then for future, I need to change also other coordinates, which I will use. But at the moment, I change coordinate u only. And then I take 2 times I, imaginary. And then I have this modified Bessel in the point 2 square root of x. Then the series which represented much more nicer and much more simple, which I will denote or phi2 or sometimes g2. This is my hypergeometric function. And this usually, this holomorphic solution, sometimes people call solution of 2 Klosterman equation because it has a theoretic number interpretation. And then the corresponding equation, which is Klosterman equation, it's my 2 Bessel, which I call 2 Bessel without good reasons for this, because standard Bessel is this. And the 2 Bessel or Klosterman, it defines, it differs from modified Bessel by sign. You see, that's this and this. Well, by sign, it's differed by square. If you write it in terms of theta, you will have the difference by sign. Okay, so the operator for lambda equal to 1, if you take lambda equal to 1, you obtain operator d1, and this operator Buchstaber and called invariant shift operator. They defined the shift operator, and this shift operator commuted with this invariant operator of order 2 d1 with an eigenvalues 1. And this was the reason why they proved this multiplication formula. Namely, let's consider the shift operator T u nu, which correspond to my operator d1. So I take the series over this d1, I put d1 in this series, and this series, it's Bessel-like, this Bessel-like series. So I obtain this series, and then I can interpret it like radial part of Laplacian operator on R2 in polar coordinates. So I can think that U is my radius, and then it is radial part of Laplacian on the plane, and then this Laplacian acts in the following form with the help of this D1 operator. So we obtain, solving the eigenvalue, we obtain that this shift operator with Laplacian define the product for Bessel function in the point mu square root of lambda, u square root of lambda. This is the shift operator formula. It's a simple demonstration how to get Sonnen-Gegenbauer formula from the shift operator property. Now we can apply theory.
Sorry, why it's called shift operator?
Because it is terminology which belongs to Delsart and Levitan, shift or translation operator, or generalized shift, generalized translation operators. These operators of generalized shift, this typical example of such operator, it's the simplest operator of generalized shift is just this one. It's the simplest. it's a translation or shift operator. And then people ask how to define the more complicated shift operators. The theory of two-valued group, which I will speak about, gives you another example of such shift operators with the help of this kernel for Bessel 2. So Bessel story, which I want to tell
Seems
you.
that here you have almost D1 operator in the brackets, right? It's not just, it's not D1 here in the formula.
No, if you can if you put u.
So you change the
You see,
yeah, but I mean
it's just interpretation for this.
it's almost this operator, right? It's almost this up to this.
Almost. Yeah, and then I put this observation that if I apply the mean value theorem to circle, then this product can be written the integral of the same function, but in this formula with the help of cosine theorem with some measure phi over circle. It's a very simple proof. Let's introduce a third coordinate w, which is square root of this cosine theorem expression. And then we can write our product like the integral of g0 of w times square root of lambda d phi. But the measure form d phi.
I'm sorry, how do you obtain this formula for the product? The first one, when you integrate along the circle.
This is the
no, the one in the next page, in the next slide.
This one.
Yeah, this one in the bottom. In the bottom, lower. Even lower.
This one.
Yeah, is it just the same? Is it just the same formula? But how do you obtain?
It is just the same formula. I replace square root by w.
So you don't derive this formula. It's kind of given, right?
It's just a mean value theorem for this.
Don't quite understand this because on the right they have product of two elements. On the right they have. I don't quite understand. Mean value means you integrate, you get something which is equal to the derivative times the length of the curve.
I want to prove it. I want to prove it.
This formula.
Yes.
And how? But you begin with the formula which is almost as mysterious as the first one. We just replace this.
I mean this operator. It's a shift. This operator. It's my shift operator.
Right.
Right. On the other hand, this operator, left hand side, it is the series of this.
So how is it? How do you obtain the equation that the shift operator applied to the Bessel function is equal to the product of two Bessel functions? It's just the shift. I don't quite understand this.
It's a well. It's a there is a theorem of there is a theorem of Delsart, and then it is generalized by Levitan about how to get for shift operators such type of formulas from Sturm-Liouville type operator.
I see. Okay, I see.
And this is a result of this theorem.
Yeah. You can just give it.
If you want this operator D1, it's a long story. This operator D1 can be interpreted like the first infinitesimal Lie operator for generalized group defined by the shift operators, and it is quite in detail written in the book of Levitan, or if you want, in his paper in Russian math service. But
I see.
it is just
Okay. So we begin with this formula actually, there, right? for this.
And then I want to interpret this formula like multiplication formula. I mean, like multiplication kernel formula. For this, I want to make very straightforward computation. I go to change of variables with this W, and this W differential dW I express via a differential of phi with this sine coefficient and this cosine theorem under the square. And then you see that we have this formula for area of triangle. We're using this sine and cosine theorem. So we can express it like W dW divided by 2 square root of triangle like this, with U, V, and W is the edges of this triangle. And then use the observation that we can replace our square like square root of polynomial of degree 4 in half perimeter. This. So we have this Heron formula. And this Heron formula gives you exactly the expression which we need. Look, here we have products of 2 Bessel function, and here we have this JW square root of lambda divided by square root of Heron expression. So this, our kernel polynomial, can be now factorized if we replace U, V, and W by their squares. We remember that for the product of Bessel function, we had here measure with W. So we need here have the expression of degree 4, and we have it. So this is an exact correspondence between a Sonnen-Gegenbauer formula for Bessel function G0 and this two interpretations of shift operators in terms of product and in terms of integral of mean value theory. So this is this classical story, and what we did, we consider so this Heron configuration, it is just geometric interpretation of zeros of this kernel. You remember that this square of triangle, it is a product of 4 factors, and these 4 factors means that you have 3 lines, and in midpoints where the inscribed circle in this triangle we have points 0, 1, 1 in projective homogeneous coordinates in midpoints, and this I want to generalize for n case. What n Bessel operator or n quantum operator? This is the equation of such form. So theta, now it's theta to n. Lambda I have also take in the degree n, and I have this eigenvalue problem with lambda. And also we can go from this nth order differential operator to system with first order operator, and we can consider this like a connection in some trivial bundle I don't want to speak about the quantum homology operator, but in fact, this representation, it is typically a typical example of Dubrovin connection in this story of quantum Pn-1 operator. So we have this operator with matrix like this lambda in the low left angle, and we have 1, 1, 1 over diagonal. And if I take lambda equal to 1, then my connection, as it was in the case n equal to 2, has regular singularity at x equal to 1. All unipotent monodromy defined by this structure of connection. And we have only one Jordan block for this. And the second singularity will be in infinity, and it is irregular singularity. I will not say more about that, only that the eigenvalues of monodromies in infinity we can compute by this formula, but it is irregular. What is beautiful, if we take now such Laurent polynomial in n variables, z1 plus zn plus x as a parameter divided over product of z n, then taking the following function gn x lambda, exponential of my Laurent polynomial times the historic measure, and the integral we take over n-1 dimensional torus. Then this formula gives you the following representation as a formal series, and this is a generalization of the generated hypergeometric function 0n f with n plus 1 gamma n plus 1 gamma n plus 1 n factorials. So this is the n factorials in the denominator and 1 in numerator, and lambda x as a lambda x over factorial in variables. This gn function, it is exactly solution of our equation with this operator. This is the n Bessel function. If I take now lambda equal to 1 and take the product of these two functions in x and y, then I obtain generalization of my formula in series, and I have double series in x and y in n and m, which has again binomial coefficients. It's a formal series. I don't want at the moment say about radius something, but if I multiply this series by z2 minus m plus 1, it means that we can expand it in power of z, this product. I can represent this product in terms of Cauchy type residue formula. So it's a dz over z, some kernel times gn of z. My kernel, which is now can be also written in terms of some series, it is homogeneous, so I can write it as a function of big X and Y, which is X over Z, Y over Z. And then in this affine X and Y, my kernel function has the form n plus n m to degree m, xm, xy. It is a formal series. Then what we prove that for this function, we can find the corresponding Heron configuration, like we prove it for n equal to 2, this decomposition of kernel in this product. Then there is a kernel decomposition for any n. And this kernel starts with x to n, y to n, z to n, plus other terms, but we can factorize this as a product of x, y, and z, and coefficients of y and z, omega and eta, they ran over all n's root of unity. So there is a lattice of roots of unity, and my kernel degeneration in front of this equation can be developed in this product. And this kernel, this kernel degeneration, it is a rational curve R n. Degree of this curve is n minus 1, n minus 2 over 2. And this beautiful result, it's a beautiful result, means something for n-valued group, like our decomposition of Heron means something for two-valued group. We will see what it is exactly means. If I compute these polynomials for small value n, then for n equal to 3, my function will be this cubic x minus z plus y to 3 plus 27 of x, y, z. And you can factorize it in the product of some using cubic root of unity in the product of linear terms. And then for n equal to 4, this is a quartic, and this quartic also may be written. For example, you see our for n equal to 2, our under radical expression, Heron expression, can be written in this form, and this one has a symmetric form because it's sigma 1 and it's sigma 2, and all these polynomials, they are symmetric and they factorize. This means, for example, for n equal 4, the following mean. I took U4, V4, W4, like I took U square, V square, W square in the case n equal to 2. Then I obtained product of linear terms and product of quadratics. But each quadratic I can factorize going to complex numbers. So each conic can be splitted for product of linear terms with complex coefficients. So in projective plane over C with coordinates U, V, and W, we have configuration of 16 lines for the case of n equal to 4. And all these configurations, they are depend on the square roots of 4. And this is true for any n. That's one of our results. Now let's look what's happened if you take analog of Clausen duplication for any n. So you have this square product of Bessel function at the same point x. You have again coefficients which are binomial, and you can interpret this duplication formula using so-called Hadamard convolution. Hadamard convolution of two series, it's operation which gives you again a series for Hadamard product of this function, such that the coefficients of this series are corresponding products So this convolution, it means that you take these coefficients in the degree j of x in the degree j of x, and you take in front of j of x products of the corresponding coefficients. In integral form, it is exactly a generalization of what formula we saw for n equal to 2. So we have usual multiplicative convolution, and the square of my n Bessel solution, it is just a convolution with some function which is nothing but our kernel taken in the same point x equal to y. And we have generating coefficients from this series Cn for this. Now I want to make some reminder about multiplication structure of integrals. So if I take, for example, set of polynomials of one variable, and these polynomials have, so it means it's kind of basis in polynomial ring. So I will take P01, any polynomial Pi has degree I. And then I can write product Pi and Pj with the help of the structure constantCijk. Yes, so I have this product structure, and then using the language of generating functions, say take f lambda x like a generating function for my basis polynomial, then the kernel representation for this constant, it is just a series over series form in x and y with measure dz over zk plus 1. So it's one form in z, if you write it. And product can be easily computed using the this one form and Cauchy residue. This lemma was proved by Odesky and Kontsevich, and this approach also hints that we can, instead of one parameter lambda, can consider polynomials in any parameter. So we can generalize a multiplication of formulas for instead of binary operators for n-ry product operators, and we obtain multi-nomial kernels. That's what we also did in our work with Ilya and Dukov and Straton. In terms of this kernel series, which we write now in Odesky and Kontsevich form for our Bessel, we prove the following very nice theorem. If we take this family of hypersurfaces in n- dimensional torus, algebraic torus, then this surface of this type, which depend on three parameters, z, x, and y, and big Y, they are coordinates in this torus space, and in this hypersurfaces in torus, then we can define the period of this hypersurface using the following Poincaré residue form: 1 over double Wn in coordinates x over z, y over z. 1, we just write it in affine coordinates with this toric measure. And then we prove that this period formula exactly corresponds to series expression for n Bessel. So this series, it is gives you the period of this hypersurface in dimension n-1. That's what I wanted to say about Bessel. Now, how to come from Bessel to Buchstaber and Kontsevich, because I slightly forgot about Buchstaber and Kontsevich, but in fact, no. I want just to remind what means two-valued group. Two-valued group, it's just a set with two-valued multiplication law star, which assigned to pair X elements from X, element of symmetric square of X. And also this operation has some unit element E and inverse with respect to this law. Associativity means that if you take three elements from our set X, then we have four elements set X star Y and then Z, and X and Y star Z in this order. And this element set coincide. Four element set coincide. Then what means unity element? It means that if you have some element E, then for any X, this law gives you the same element in symmetric two-set element in symmetric square if you take it from left and to right. We will call it strong unity. And inverse, it means that if you have two set X times X2 minus 1 and X2 minus 1 times X, these two set elements contain our neutral or unity element E. The simplest example of
When
such
you say it contains, if you say it contains E, you mean that they have the form E comma A and A comma E?
Oh,
What do you mean contains E?
Hmm?
If you say contains E, do you mean that each of these has the form E comma A or
Yeah,
A comma E?
I mean, when you speak about inverse.
Yeah, I'm just trying to understand what it means to say, because this thing is an element of X times X. It's an element of the product.
This strong unity means that if you take some element, any element,
Not the strong unity, the next one, the inverse.
Exist inverse. That's what my question. You speak about this.
Yeah.
So it ends up in not in symmetric product, but rather in set of pairs of elements.
Yes.
So the pair which corresponds to the E times X is of the form E and something.
It means that in this set X times X star X2 minus 1 contains natural element in symmetric.
I just wonder, what does it mean contains? Because
The pair,
E is an element of X, and the product could be an element of X times X, symmetric.
It means that or one or two or left or right contain it is E. It is one. Or E. Look, the example it's very
You don't have addition in it. You don't have addition in X, do you?
What?
So it's not E comma E, right?
No,
Can
it's
it
not
be?
E comma E.
It's symmetric.
It is not E comma E.
no, I mean symmetric means you should actually interpret it not just as a symmetric product, but rather as a set of pairs, unordered pairs of elements in X.
Right.
So the pair which you obtain from X star X minus 1 is of the form E and something else.
And then
Yes.
it will not be symmetric. The right-hand side is supposed to
No,
be
there is no
symmetric.
right and left. It is
No.
just symmetric. It is just a pair.
Well, at the top of this slide, which is hidden now, it's written that the map is that this star maps to the symmetric.
Yeah, but symmetric means just a set of pairs.
It's just a set. It's not, you know.
Sim squared is not.
It means that it doesn't matter which order you take.
Okay.
Let us see the simplest example. This
In
is
an example, great.
yes, it's a great example. You see, let's see, consider C with the addition operation, and just this order 2 automorphism, which I denote by epsilon square equal to 1. So z to epsilon z. Then I can take on the quotient C over Z2 this two-valued group structure. What the star operation multiplication law for x and y gives? It gives you the following. You have square root of x plus square root of y squared, and the difference square root of x minus square root of y squared. The unity is just usual 0, and each element is inverse of itself.
Okay.
Okay?
Mhm.
It is just inverse of itself. And then we have the application C, S. And this application to each pair Z1, Z2, we can assign the symmetric function of Z1, Z2, sigma 1 and sigma 2. Then we can interpret this operation as a roots of the following quadratic polynomial. Let's consider the quadratic polynomial with coefficients x plus y and x minus y squared, and polynomial is quadratic with respect to z. Then we can rewrite it in terms of symmetric function sigma 1 and sigma 2. And then you see that we can in this polynomial f replace any variable by any. It means we can consider it like quadratic in z, but we can consider it like quadratic in x and like quadratic in y. And this polynomial has discriminant type. So we can define this multiplication law, which I described, as the following. It is just a pair of roots, this polynomial with respect to z. So we have z minus x to inverse square root of y inverse, but they are the same x and y, and here the same x and y. So we have set 1 and set 2. That set 1, it is square root of x minus square root of y in square, and the second, it is square root of x plus square root of y in square. And this operation, it is the same like operation x and y. It is just my multiplication law, which I define. So,
Sorry, what is epsilon here?
huh?
This example, what is epsilon here?
It's plus minus 1.
You just send.
You can write here instead of minus, you can write plus epsilon.
Yeah, what is epsilon?
Plus minus
Epsilon is
1.
just some number, just -1. I see. Okay.
Plus minus 1. You just
Thank you.
you will see now.
I see.
Okay, you will see a little bit later for n valued law. You can generalize it for for nth root of unity.
I see. Thanks. Yeah.
Now, what is a two valued formal group law? So now we go to any commutative ring, for example, Z, R, or C, and we consider the polynomial rings also, if you want it as a basic ring R. Then we consider formal series with over this commutative ring, and the formal series phi of two elements U and V, we can call a formal series, and we say that it is a classical formal group over R if it starts for v equal to 0 from u and satisfy this property which we call associativity. It means that if we replace v by phi of vw, and then we replace u by phi uv, we obtain the same from left and from right. For example, Buchstaber polynomials, which I described, it is a special kind of this polynomial construction. Namely, let's consider the second order quadratic polynomial in Z, and coefficients theta 1, theta 2 are formal series over R. This theta 1 of xy, theta 2 of xy. And we suppose that we have two roots, Z1, Z plus, Z minus, and our series is they are sum and product of this Z plus, Z minus, such that this Z plus and Z minus, these roots, they are not any, but they are square of module of some formal series phi of uv, and square of module of the series of y bar of b. So we have some involution or some, let's suppose that we are over C. So we have this square module and this square module. Buchstaber and Novikov, they call such two-valued groups square module type group. So we suppose that phi initially some formal group, initially. Then knowing this formal group, we can construct a new formal group using this Z plus and Z minus. What we have as an example. First example, it's our favorite conic x squared plus y squared plus x squared plus y squared plus z squared minus 2 times xy minus 2 times xz minus 2 times yz. This conic, it is typical Buchstaber polynomial which correspond to quadratic module construction if we take initial formal group u plus v. And this example of two formal group, Novikov and Buchstaber found when they describe the spectrum of usual homologies. So in usual homologies, you have this quadratic modular formal group starting with usual sum formal group phi. If we consider phi more complicated, starting with u plus v minus some q uv, that type of square module formal group Buchstaber discovered in K-theory. And the corresponding polynomial, this polynomial b, it is polynomial, it's a cubic. It's a cubic with coefficient q squared and in front of cubic term, and quadratic term is it's our old cubic and new our old conic, and this q square xyz. This is a fine coordinates, a fine form of Cayley nodal cubic surface in P3. Then, a part of cohomology and K-theory, in 80s, people started to study so-called elliptic genus and elliptic genera. Elliptic genera, it came from physics. Well, I don't want to go into details, but it was a necessity to describe elliptic formal group law, which correspond to this elliptic cohomology of Witt and other people. Then Buchstaber, in his paper 1990, introduced this Buchstaber polynomial, which I studied in my introduction. The parameters of this Buchstaber polynomial A1, A2, A3, he cleverly chose with the help of some elliptic curve. Let's consider elliptic curve in Weierstrass representation. V square equal to 4u cubed minus G2u minus G3, and then take a point alpha on this cubic and take p function, Weierstrass p function in the point alpha. Then the first coefficient will be 3 times p alpha. The second coefficient A2, it will be 3 times p alpha square minus G2 over 4, well, this modular parameters. And A3 will be 1 over 4 for p alpha cube minus G2 p alpha minus G3. So we just took the special representation for our parameters A1, A2, A3. And then Buchstaber proved.
Just one question. Is this the formal group law which you obtained from elliptical homology, right?
Yes. Yes.
Okay.
That's what at least I understood from the paper of Buchstaber and Bessel.
Okay, I see.
So they proved the following theorem. The discriminant multiplication law with elliptic parameterization, which I described before, can be reduced to the usual addition law, very abelian addition law, x plus minus y plus minus z equal to 0, if you take the following change of variables. Namely, you introduce this x, y, and z, big one, like 1 over p function in big X plus p function in alpha, p function in y plus p in alpha, and p function in z plus p in alpha. And this inversion will be our x, y, and z. So if we replace x, y, and z in this function, we obtain the following law. The proof which Buchstaber and Bessel proposed based on the observation that if we take one coefficient A1 equal to 0, so we take alpha such P of alpha equal to 0, and other coefficients will be modular parameters times minus 1 over 4, then this simple simplification of Buchstaber polynomial gives you polynomial which correspond to Kontsevich polynomial. And they didn't discover that it was when I read this paper, I said, oh, but this is it is Kontsevich polynomial. Look, Buchstaber polynomial starts with sum, and here you have this product. But if they take special value of alpha such p of alpha equal to 0, then the corresponding polynomial gives you Kontsevich polynomial for special value of parameters. And this Kontsevich polynomial came from this story of Haken. So it was a starting point of my reflection how they should relate. Then I introduced this, I told you, this generalized Kontsevich. I wrote it in the quadratic form like Buchstaber likes. And then I consider this trinomial with monic trinomial. And then it is not difficult to see that the addition theorem, it is exactly the condition of this addition law on cubic. It gives you the that's what addition law of Bessel and Buchstaber theorem. And then it was not difficult to verify the following results. So we want to describe, namely, to find necessary and sufficient conditions for polynomial of 3 variables such that if we have zero loci of this polynomial, we have two-valued group law, first. Second, we want this polynomial to be discriminant type. It means that if this polynomial discriminant type, when this discriminant type polynomial coincide with the generalized Kontsevich polynomial for some values of parameters. And then what necessary and sufficient conditions that my discriminant type polynomial also factorize in product of polynomials in one variable, like for example for z in x and y, for x and in z and y, etc. And these three problems, they form some kind of triangle. We can go from one problem to another problem because we know this Buchstaber Vesselov theorem, and also we prove some conditions in our paper, which technical conditions which I don't want to precise now. But as a result, we obtain the following theorem: generalized Kontsevich polynomial. It is factorized like this, with the same cubic from which we start. And due to symmetry, it is it is strongly discriminant. And as a result of this is what I don't want to discuss, but I can discuss it in another day if you want. As a result to this Kontsevich polynomial, we can assign some generalized Kovalevsky type integrable integrable system. It is more precisely, it is an integrable system of Komarov-Kuznetsov type. And then, if we take the following change of variables, namely, we replace in Kontsevich polynomial x, y, and z by inverse, and identify the coefficients a1, a2, a3 with a, b, c, then after multiplication by Jacobian of this transformation, x, y, z squared, we obtain exactly Buchstaber polynomial. And Buchstaber polynomial in its turn can be factorized also in cubic, but in fact it factorized not in cubic, it factorized in quartic, but it's reduced quartic with 0 free term. So we have x times cubic, y times cubic. And this cubic are evidently inverse to Kontsevich cube. And one of our theorems is the following, that all symmetric polynomials in three variables of degree 2, which satisfy formal group identity property, they are coincide with Buchstaber-Kontsevich type polynomial for some values of parameters. So this family covers all group laws and the transformation which describes this group laws, it's transformation with change zero element. For example, between Buchstaber and Kontsevich polynomials, the difference is the following: identity in one case, it's a north pole of sphere P1, and identity of second, it's south pole of P1. And for other group laws, we can take any point on sphere, considering, say, twistor sphere, and for any psi in this sphere, we can find a group law. What beyond? Very quickly. Beyond, we have n-valued group laws. Instead of second, n equal to two-valued group law, we can consider n-valued group law. And associativity, generalized, unit element generalized, and inverse element. So after corresponding definition, we can find n-valued group structures on C. And these n-valued group structures on C are parameterized by Buchstaber Riesz polynomial, And these Buchstaber, these polynomials are our kernels. It's our singular sets of our kernels, which I showed you before. That's all. Thank you very much for today. What I didn't tell you, I didn't tell you the story of Lenglen's. I didn't tell you the story of combinatorics. I didn't tell you the story of well, very nice story about mirror symmetry.
Yes, it seemed that everything was quite close related to the mirror symmetry. The polynomials you wrote
Yeah.
looked like the functions which should be in mirror symmetry. So if you want to continue next time, I think, or in
We will discuss, Gosha, probably not next
let me
time,
know.
in 1 week.
Okay.
Okay.
It's beautiful. Yeah, that's it. Very interesting.
Very interesting.
Especially these connections to mirror symmetry.
It's very interesting, actually.
By the way, or maybe.
Okay, excuse me, also, I should go now.
Yeah.
Okay.
So in that case, we just need to thank
Gosha, today is 5:12, I'm busy, but 19, I can continue.
Yeah, it would be great. I think we'll,
Okay.
next time we'll have Sasha Chervov.
Bye.
By the way, Sasha Chervov will speak next time.
Okay, bye.
Bye.
Okay, bye.
Sorry. So then we not even thank our speaker because he is gone.
Yeah.
Let's say goodbye to each other and see you next Tuesday.
Okay.
Yeah.
Yeah.
Okay.
Bye.
Bye.
Then finish the session.
Yeah, I think we cannot because it's automatic. It's not. I'm not actually the owner of this session. We need to leave everybody. I'm not the owner of this
Okay.
account. It's just
Yeah,
it's
bye.
an account which belongs to the independent university. So I cannot
see.
leave this. I cannot stop it.
Okay.
Okay.
Then bye.
Bye.